Hello and welcome. Today, we're diving into a class of organic compounds that are, well, pretty much everywhere, but they often fly under the radar. We're talking about amines, the true unsung heroes of the chemical world.
So let's kick things off with a little puzzle. What do you think is the hidden link between the medicines that keep us healthy and the beautiful colors that just pop in our daily lives? It seems like they're worlds apart, right? But the answer is actually a single, surprisingly simple family of molecules. And there it is. The connection is a family of compounds called amines. They're literally the chemical backbone for so much of our world. I mean, in medicine, you've got everything from the adrenaline our bodies produce naturally to the antihistamine Benadryl, and even the anesthetic Novocaine you get at the dentist. And it doesn't stop there. They're fundamental to hormones, vitamins, super durable polymers, and yep, those very dyes we just mentioned. Okay, so it's pretty clear these compounds are all around us. So for the rest of this explainer, let's pull back the curtain and really figure out what makes these chemical heroes tick. We'll start with the basics. So what exactly is an amine? Well, at its core, it's actually really simple. Just picture an ammonia molecule. That's one nitrogen atom bonded to three hydrogens. Amines are just what you get when you swap out one, two, or even all three of those hydrogens for other carbon-based groups. So you can think of them as just modified ammonia molecules. And their shape is absolutely key to how they work. Just like their parent, ammonia, the nitrogen atom in an amine sits right at the top of a little pyramid. This specific 3D structure is really important because it leaves a pair of electrons totally exposed and ready to react. And that reactivity, that's precisely what makes them so incredibly useful. With so many different kinds of amines, you might be wondering, how do chemists even keep them all organized? Well, they use a classification system that's kind of like a family tree, with good old ammonia as the original ancestor. And this is basically how that family tree works. You start with ammonia. Now, if you replace just one of its hydrogen atoms, you get what we call a primary amine. Go ahead and replace a second one, and you've got yourself a secondary amine. And if you replace all three, you guessed it, you form a tertiary amine. It's really that straightforward. Primary, secondary, tertiary. It all just depends on how many hydrogens got swapped out. All right, so we can classify them on paper, no problem. But what if you're in a lab? How can you tell them apart? How do you know if you're dealing with a primary, secondary, or tertiary amine? Well, it turns out there's a classic and kind of smelly test for that. This test is called the carbylamine reaction, or you might hear it called the isocyanide test. Its whole purpose is to give you a really clear, unmistakable signal if a primary amine is present, because secondary and tertiary amines, they just won't react in the same way. So here's how it works. You take your mystery sample and you heat it up with some chloroform and potassium hydroxide. If you have a primary amine in there, it's going to produce a compound called an isocyanide. And trust me, you will know if you've made one. Why? Because isocyanides have this notoriously awful, unforgettable smell. So if you get that horrible odor, congratulations, you've got a primary amine. No smell? Then you're dealing with a secondary or tertiary one. It's a simple, if a bit pungent, way to get a clear answer. Okay, now we get to where amines show their real superpower, building other complex molecules. When a primary amine is attached to a stable carbon ring, what chemists call an aromatic amine, and it reacts under just the right conditions, it forms something called a diazonium salt. And these salts, they're like a master key for chemical synthesis. But hey, don't just take my word for it. It's well known that diazonium salts are incredibly valuable intermediates. They basically open up a whole new world of possibilities for adding different groups onto an aromatic ring, which is often really, really hard to do directly. And this is what that master key unlocks. That diazonium salt acts like a perfect little attachment point. It can be easily swapped out for all sorts of useful groups, things like fluorine or even a cyano group. This is huge in areas like drug development, for instance, where adding just one of these atoms to a molecule can be the difference between a useless compound and a life-saving medicine. It gives chemists an amazing level of control. And now, let's bring it full circle. This exact chemistry, specifically something called a coupling reaction that involves these diazonium salts, is how we get a huge class of vibrant, colorful compounds called azodyes, the very same dyes we talked about right at the start. It all comes back to the unique power of amines. So after all that, let's just zoom out for a second and recap the most important takeaways. Why are these little molecules so incredibly essential? The main thing to remember is this. Amines are so much more than just a topic in a textbook.
They're foundational to life itself. They're the building blocks of proteins and hormones. They are absolutely crucial for modern medicine and materials. And as we've seen, they're the gateway to amazing synthetic tools like disonium salts, that chemical master key that unlocks the entire world of color around us. So I'll leave you with a final thought to chew on. Amines have already given us so much, from life-saving drugs to the most brilliant dyes. Now that you know a little more about their power and versatility, what do you think the next great innovation built on amine chemistry will be? Thanks so much for joining me for this explainer.